Good morning, everyone. I heartily welcome you all online refresher course in chemistry hosted by Department of Chemistry, School of Sciences, Gujarat University, Ahmedabad on behalf of Dr. Jagdish Joshi, Professor, Director, UGC HRDC, and Dr. Dilip Vasawa, Assistant Professor, Refresher Course Coordinator, Department of Chemistry, School of Sciences, Gujarat University.
Welcome all. I am Siddhi Panchal from Department of Chemistry, School of Sciences, Gujarat University. In the next session, we would encounter Dr. Rajesh Kamble, Professor, Department of Chemistry, University of Mumbai. He is having 20 years of experience in teaching and research. His thrust area of research interest include designing, synthesis, and characterization of novel AIE functional organic materials for application in OLEDs, solar cells as chemosensor and for bioimaging purpose. He has done supervision of 84 MSc projects, has guided 2 PhD students, and currently have 6 PhD candidates under his guidance. He has fruitfully completed 3 research projects funded by UGC, DST SERB, India. He has total 33 publications with 6 national and 27 international. Moreover, he is reviewer for journals like RSC Advances, Chemistry Select, New Journal of Chemistry, Journal of Material Chemistry, Journal of Molecular Structure, Journal of Chemical Sciences, and many more. He has also presented 40 papers and conferences at national and international level. He has delivered 11 lectures at various universities, research institutes, in conferences. Additionally, he was secretary of UGC SEP-sponsored National Conference on Research Development in Chemical Sciences 2018. He has also served as coordinator of refresher courses and worked as coordinator of IQAC in various committees at university level.
Dear participants, myself, Dr. Rajesh Kamble from Department of Chemistry, University of Mumbai. It's my pleasure to deliver a talk in UGC-sponsored second online refresher course in chemistry organized by UGC HRDC and Department of Chemistry of Gujarat University. Let me thank first of all Dr. Jagdish Joshi, Professor and Director of UGC HRDC, Gujarat University, and the course coordinator, Dr. Dilip Vasawa, Department of Chemistry, Gujarat University, for giving me this opportunity to deliver my lecture in this refresher course. So the title of my talk is Carbazole-based donor acceptor functional organic materials for applications in organic electronics. So let me give about the brief outline of my talk. The discovery of organic molecules as semiconductors, classification of organic semiconductors, importance of donor acceptor architecture, so which is required in organic semiconductors, applications of organic semiconductors in different fields, current scope and development of organic semiconductors, about the phenomena aggregation-induced emission, so which plays important role in solid-state emission of these organic molecules, which have applications in optoelectronic devices or in bioimaging also. Then thermally activated delayed fluorescence and its importance of carbazole as a donor in donor acceptor assembly, and our efforts to meet present requirement in the field of organic semiconductors. Now, let me start with the brief history of organic semiconductors. Kalman and Pope, they discovered that the organic insulators become semiconducting when the charge carriers are injected from the respective electrodes. Charge means the hole, and electrons are injected into that organic insulators. What are organic semiconductors? These are the compounds whose building blocks are pi bonded molecules, or the polymers, which are made up by the carbon and hydrogen, and in some molecules that includes or that contains the heteroatoms like nitrogen, oxygen, and sulfur. Organic semiconductors, if you compare it with inorganic counterpart, these are having similar properties to the inorganic semiconductors with the holes, electron conduction layer, and a band gap. So this figure you can, everyone knows that we can classify the metals, semiconductors, and the insulators on the basis of their band gap. Okay, the valence and the conduction band and the band gap within them. So metal, they have a very negligible band gap. Semiconductors, the moderate, and insulator, they have the large band gap. Further, these trio, McDiarmid, Shirakawa, and Alan Jaeger, they reported high conductivity in oxidized and iodine-doped polyacetylene. It's a long chain molecule in 1973. And this is the breakthrough. And for this conducting polyacetylene, this breakthrough, they were awarded Nobel Prize in Chemistry in 2000. Followed by Tang and Vance Lyke from Kodak Laboratory. They fabricated the first organic electrolysis device, that is OLED, in 1987. And that was the first application of such kind of molecules, organic, fluorescent, and semiconducting molecules, as organic light emitting diode, or OLED. And the world's first OLED television, introduced by Sony in 2007. This you can see, this the first television, OLED television, made by or produced by Sony. So with that brief history, let's see the classification of these organic semiconductors. How these organic molecules are classified based on their molecular weight and the electronic properties. Like on the basis of molecular weight, organic semiconductors, these are classified into small molecules or oligomers. These are the small molecules, like examples are perfluoropentasine, tryptophan, and this. And the polymer or the large chain molecules. For example, the polythiophene and polyphenylene, vinylene. On the basis of their electronic properties, these semiconductors are typed into P-type, or the hole transporter, N-type, these are electron transporters, and the ambipolar, which transport both the charges, means which can act as a P as well as N-type materials. So this is the classification of organic semiconductors. Now, why organic semiconducting materials are beneficial over the counterpart, that is inorganic materials, or inorganic semiconductors, which are mostly used in electronic devices, electronics, that is silicon. Popular is silicon. Now, organic semiconducting materials, they have many more benefits as compared to inorganic semiconductors because of their low molecular weight, simple structure. The route of synthesis of such compounds is easy. It can be purified easily, and we get these compounds in their high purity. Reproducibility is there, and the ease of structure modification. The structure modification can be done easily to tune the optical electrochemical properties. And the solution processability is better in case of these organic semiconducting molecules or materials because they are soluble in many organic solvents. You can see this picture here. A foldable OLED screen is what made. Now let's see about the role of donor acceptor type architecture in organic semiconducting dyes. So importance of DA architecture in such molecules. Now DA molecules have been extensively synthesized and investigated in last few decades because of their potential application in the field of OLEDs, organic field effect transistors, photovoltaics, RFIDs, organic lasers, because of their unique charge transfer properties. You can see this. Many more applications of this DA architecture, okay, to get these organic semiconducting molecules. Okay, there we can see it facilitates the ICT, intramolecular charge transfer. Decrease in band gap, small band gap is required. We have the facility to structure modification. We can add a donor acceptor type to the polycyclic, okay, units and make it a one which extend the conjugation and responsible for active charge transfer, that is the hole and electron. This DA architecture also allow to tune the photophysical, electrochemical, as well as the thermal properties. This DA helps to induce the AIE property, aggregation-induced emission property, which is one of the important phenomena that came into picture in 2001. In the molecule to obtain solid-state emissive materials. And we can get the good thermal stability in case of this DA type of molecules. So these are some main importance of this DA type of molecules in organic semiconducting dyes. Applications of organic semiconductors are in various fields of this optoelectronic area of devices. This can be used as OLEDs, organic light emitting diodes, in RFIDs, as organic lasers, as organic photovoltaics and solar cells, and in organic field effect transistors. So wide applications of these organic semiconductors. Now, after the application part of these organic dyes or semiconducting dyes, let's talk about this phenomena, that is aggregation-induced emission. Now, to obtain AIE activity or property phenomena in the molecules for their solid state application in organic electronics. So what is AIE? AIE is an interesting photophysical property or phenomena in which molecules are non-luminescent in their dilute solutions, but become highly emissive in their aggregate or the solid state by phenomena that is called as RIR effect, restricted intramolecular rotation effect. I'll come to that point in the next slide. AIE overcome aggregation concentration quenching. Now this is very detrimental phenomena Ultimately, these kind of molecules are used in their solid state in the organic electronics. Even though the molecules, these organic molecules are emissive in their solution form, but when you make a film of these molecules, so there we can see this detrimental effect, that is aggregation cause quenching, ACQ, or aggregation concentration quenching. When the molecules comes closer to each other and get aggregated, so because of pi-pi stacking or see the other type of effect, the emission quenches. And that is explained by the Tang and al. In 2001. So conditions for molecule to be AI active. They should be non-planar in conformation, propeller in shape, and there must be a restriction to the intramolecular rotation or vibration or rotation plus vibrational motion in the solid state. Now, this you can see here, HPS, this is the hexaphenyl silol. Silol is what is centrally placed here. Silol, it acts as a stator. And 6 phenyl rings attached to this silol, it can rotate. These can rotate, rotatable phenyl rings. This hexaphenyl silol is non-emissive in its solution state. When it is dissolved in some organic solvent, it cannot show the emission because of free rotation of these 6 phenyl rings, and they make a planarity. But when it aggregates, then this RIR effect can be seen. There is restriction on the intramolecular rotation of these 6 phenyl rings in the solid state or aggregated state. And that is the RIR effect. Because of that, in aggregate state, this hexaphenyl silol is highly emissive. And the arrangement of this molecule, intramolecular, see the interaction is like this. It's in the propeller shape. It's not a planar one. So let's talk more on this. What is the principle behind this AI activity? Now, planar geometry for molecule is a planar tend to aggregate as disk pile up. That's one method. Okay, disk pile up. And that is due to the strong pi-pi stacking interactions between the aromatic rings, which commonly turn off the light emission. For example is the perylene. It's a 5-member ring. Okay, it's a planar. Geometry is a planar. This is emissive in solution state. But when it aggregates, because of this pi-pi stacking or the interaction, it shows the ACQ effect, that is aggregation cause quenching effect. It becomes non-emissive, or the emission turns off in solid state. But on the other hand, the non-planar or twisted luminophore, due to the restriction of the intramolecular rotation, that is RIR, of the multiple phenyl rotors, just as I said in the first slide, this is the hexaphenyl silol. Silol is centrally placed, it acts as a stator, and the 6 phenyl rings are the rotors which can rotate. These rotates against the stator, that is accepted. In the aggregate state, light emissions turn on by aggregate formation, and hence we can get to the AI property. Now in solution state, this hexaphenyl silol, because of the rotation of the 6 phenyl rings, it is non-emissive. But when it aggregates, it has this non-planar geometry. There is restriction on the rotation of the 6 phenyl rings. And such type of this, now the packing is observed, propeller shape. And this molecule, it becomes emissive on its aggregation and solid state. So thus this hexafenilcyclone is having, see, the greater importance, okay, because ultimately we use such molecules in their solid state. Like for example, in case of OLED. Now other molecules, if you see, the simple, like see the fluorescence is a dye. It's a highly emissive dye in the solution state, a green image. It is highly emissive in its solution state, but when it aggregates, because of pi-pi stacking interaction, so this ring is what a planar one, you can see here. Pi-pi stacking in its aggregate state or solid state, it is non-emissive. Another example is a tetraphenylethene, tetraphenyl 4-phenyl rings, ethene. Central stator is ethene and 4-phenyl rotatable rings. It's like a hexaphenylcyclone. In its solution state, it is non-emissive. But when it aggregates, there is propeller shaped geometry, non-planarity is there, and this molecule becomes emissive. It's a blue emitter in its solid state. So this is the principle behind aggregation-induced emission phenomenon, or this property. Now let's see about the requirement of ambipolar or n-type or electron transporting materials, which is highly required in organic electronics. Now, outstanding development in hole transporting materials, that is HTM, short form is HTM, with higher mobility than amorphous silicon is reported from last many decades. In the literature, we can see many hole transporting materials are synthesized. But there is a need of development of electron transporting materials, n-type and ambipolar, which can transport both the charges. It's lagging behind or hole transporting materials, because this n-type or ambipolar materials, their synthesis is difficult, and their sensitivity or instability under the ambient conditions, like in presence of oxygen and moisture. So that's why electron transporting materials are indispensable components of integrated circuit. And electron transport property prevails when the molecules have LUMO levels less than -3 electron volt, or the LUMO level should be between 3 to 4 electron. Now let's talk about these TDF materials. Nowadays we read many articles in the literature. A lot of work is what going on over on the world in academics as well as in industries to develop the TDF materials. What does it mean, TDF? The thermally activated delayed fluorescent material, short form is TDF. Now what are these TDF materials? Now TDF materials, these are useful in the field of organic light emitting diodes, because due to the efficient triplet exciton harvesting via reverse intersystem crossing, RISC process, from the lowest triplet T1 to the lowest singlet excited state, that is S1. Now the general phenomena, in case of the normal emission in a normal against the organic compound, when the molecule excites, the electron goes from valence band to the conduction band, that is your S0 HOMO, to the LUMO, that is singlet, your excited state. And when that electron, or we call it the exciton, comes to its ground state, it emits some light, or it shows the fluorescence. But that fluorescence quantity is what 25% only, and 75% of that exciton goes into the triplet state. And that is nothing but a loss. So to harvest it, to regain it, there is the reverse intersystem crossing process is there, that is RIS, where we can regenerate that exciton which goes in triplet state to the singlet S1. Thus, the approximately 100% that electroluminescence efficiency we can obtain. So TDF materials, these are having the low cost, carries lower pollution in your practical application, and can achieve maximum internal electroluminescence efficiency by harvesting triplet excitons, okay, into the singlet one, 100%, which is comparable with that of phosphorescent OLEDs. Now, most of the TDF materials are metal-based, organic. Metal-based is organometallics, electroluminescence molecules, while pure organic TDF emitters represent a promising pathway towards high performance, low cost, full color, and white OLED are still behind. Now, potential TDF molecules need a minimized singlet triplet energy gap. Now, we know when many of the excitons, they goes to the triplet state from S1 to triplet. If the gap is more, that gap is called as the singlet triplet energy gap. It's denoted by delta EST. If the gap is more, so then it's difficult to again recollect that excitons which goes in over a triplet state to the singlet one. But if this singlet triplet energy gap is less, it's a minimum, there it's easy to harvest that triplet exciton through RISC at a particular given temperature. So that's what's called a thermally activated loop. We do it at a different temperature. And we can use a theoretical approach also for obtaining a small delta S. In this talk, whatever the research we do in our laboratory, in our department, so we don't have this experimental facility to carry out this TADF characterization of our molecules. So we carry out the theoretical calculations for this. And we got, in some case of molecules, the small delta ST, and that can be achieved by separating the wave function distributions of the homos and groups. Computationally, it can be done. And on that basis, we can say that these molecules can be used as a TADF emitters. Now, based on the simple electron configuration theory or recipe, a number of TADF emitters with small or even vanishing, is a negligible delta ST gap. These are reported in literature, which contain highly twisted molecules composed of DA moieties. A donor acceptor kind of the architecture moieties. In such TADF emitters, both singlet and triplet states have a substantial charge transfer excitation characters. Now let's see about the Carbazole. See, in my title, see the Carbazole based this DA kind of molecules I mentioned. So why we use the Carbazole? Many reports are there in the literature where the chemists, they used Carbazole, a heterocycle, which has the possess rigid, planar, and aromatic molecular structure. It's amorphous in nature. Has the good pi conjugation. We can do the desired modification in that molecule by adding some other chromophores on that. It has a good chemical stability. It is electron donating molecule. High photoconductivity you can see in this Carbazole. You can get the excellent quantum yield and a good charge, that is the whole transporting ability. Makes this molecule Carbazole, okay, one of the important, okay, a donor molecule. Okay, so whole transporting ability of Carbazole, this means the whole transporting of the donor, electron donor, can be modulated into electron transporting, that is N-type material, by combining it with various strong electron acceptor segments. Now, locking conformation of Carbazole in DA system. Now, locking conformation is what? This Carbazole, you can see the structure. So, two benzene rings, and in between is what your spiral. 5-member having nitrogen. If this bond is what we open it, so these two phenyl rings get free. And there is again see these two phenyl rings can rotate freely. But having this bond between these two phenyl rings, okay, make it rigid. It's called locking conformation. We log this rotation of two phenyl rings. Okay, I'll come to that point in the next slide. So locking conformation of carbazole in DA system adds good aggregation-induced emission characteristics for its solid-state application in organic vehicles and mainly organic light-emitting dyes. The carbazole possesses high triplet energy and small difference between singlet and triplet energy. That is delta S, where delta S value is very small. Characteristics which are beneficial for their use as host materials for triplet emitters or thermal activated delayed fluorescence emitters and hybridized local and charge transfer, that is HLCT emitters, and so on. So the DA system formed by using a carbazole group in a molecule show the high thermal and morphological stabilities. That morphological stabilities is required in case of AI property, aggregation-induced emission property. So that directly shows us the solid state applications of such kind of molecules. Now with this brief history, then classification of these organic semiconductors, the AI phenomena, then TADF, about TADF, and the role of carbazole in DA type of molecules. Let's talk about our efforts to meet this present requirement in the field of organic electronics. Now, carbazole-based donor acceptor architecture. Now, we synthesized some molecules, 8 molecules, using carbazole as a donor with varying or different acceptor units. Now, the acceptor units like these quinoxalines. This is quinoxalane, okay, plain quinoxalane. This is quinoxalane having anthraquinone. Further, it increases its electron accepting property due to presence of 2 carbonyl groups. This ring, when it is fused, that converts into what this is the phenazine. Okay, this is another phenazine. And this is again, in case of this second molecule, this ring is what these 2 rings are fused to give this fused against this phenazine, anthraquinone, and some 3 indole quinoxalane derivatives. So this is indole quinoxalane. This is again the indole quinoxalane having 1 extra ring at this side, and this is pyridine, pyrazine indole. And R group, whatever the red you can see here, nothing but this carbazole donor. And these all moieties which are shown in blue color is can act as an acceptor unit. So thus we get see the DA kind of molecules. And let's discuss about the effect of various these acceptors and using a single carbazole as a donor on the optical, electrochemical, and theoretical properties. Now these are the molecular structures of this carbazole based donor acceptor architecture in this 1 to 8 molecule. Okay, so this carbazole is a donor and these are the various acceptors, just I told you. And this is the scheme or the reaction pathway that we used. So to get this intermediate, we use these precursors, fuse or this benzene or indole, saturated indoles, just using acetic acid reflux condition. We condense this with these various amines, diamides, and we get these intermediates, the halogenated intermediates having bromine, and then we carry it out, the Buchwald-Hartwig combination reaction of carbazole, okay, with these halogenated acceptors, and we get this desired, this all 8 molecules, okay, in their respective fields. Now let's see about the photophysical properties. That is one of the important, that is visible absorption properties of these molecules. Now this spectra, you can see here the visible absorption spectra of compounds 1 to 8. In toluene is a non-polar solvent, and this is in solid phase. Now you can see here below 400 nanometers, so whatever the high intensity transitions are observed, these are nothing but due to N to pi star and pi to pi star transitions within the molecule. And the transitions, weak transitions or lower intensity transitions above 400 nanometer, that attributed to the intramolecular charge transfer transition from carbazole donor to the acceptor. And there is alteration in ICT lambda max. Now, this ICT is very sensitive to actually on the basis of this, we can say that the molecules, these molecules have DA type of combination or the architecture. Intramolecular charge transfer transition. That means the electron transfer takes place from donor carbazole to the acceptor inwards. Now there is an alteration in intramolecular charge transfer lambda max wavelength in 1 to 8. It is based on the acceptor strength and extent of pi conjugation of acceptor. You can see the different acceptors over here. Now here you can see the pi conjugation much more as compared to this in case of 2 as compared to 1. In case of 5 also, so much more. This ring is what fused. I can see the pi conjugation increased over here. In case of indole derivatives, again, this molecule, this here is one extra thing. So increase in pi conjugation we can also. In case of phenazine, again, so these are the planar acceptor moieties, no, fused. These rings are fused, so pi conjugation is increased. So that affects on its ICT wavelength. You can see this, the bathochromic shift in that. Okay, due to extending pi conjugation, number and position of substitute carbazole donor on the acceptor segment. So here, carbazole is substituted at this position here. Okay, in case of this fourth molecule, there are 3 carbazole donors on this single acceptor. Okay, in case of this indole, quinoxaline, and in case of 6th molecule, so this carbazole is attached to this donor indole, and this is the acceptor. But in 7th and 8th, so the carbazole donor is attached to this acceptor side. Okay, here is also pyridine, pyrazine, indole, acceptor side. You can see the donor carbazole. Now, ICT lambda max in 1 and 5 follow the order rise. Like in case of 2nd and 5th, the lambda max is what you can see the red shift in lambda max, because in case of 2nd and 5th, this is a bulkier against the acceptor group, and pi conjugation is what more. So that's why the charge transfer is very fast, and that's why. So ICT lambda max, bathochromic or red shift you can see in that case, and that also hampers the quenching in emission of these 2 molecules because the charge transfer takes place very fast. In case of ICT lambda max for indole based dyes, so it varies as 7, 8, and 6. 6 in case of 6 is more, then 8 in case of 6 is more, then 8, and then 7. Why? It is more in what bathochromic shift in ICT is in 6, because this carbazole donor group is attached to this indole donor, and this is the acceptor. But in this 7th and 8th, carbazole is what substituted on the acceptor side. So in this way, you can see the slight change in what about bathochromic shift in ICT of these molecules on the basis of their the pi conjugation and the position of the carbazole attached to this acceptor. Now, bathochromic shift also can be seen in case of the solid phase due to what? The aggregation of molecules. And this is the common phenomenon. You can see the broad against this here, the peaks, okay, that goes up to 800 nanometer. You can see in case of solvent, it goes up to 550. But because of molecular aggregation in solid state, you can see the ICT, it goes up to 800 nanometer. So that is useful one. It covers all the visible spectrum, the 400 to 800 nanometer. Now in this table, you can see here the IPEA calculated theoretically by using this Gaussian software. IP stands for ionization potential, that is the HOMO level. EA stands for its electron affinity. That means the molecule, if it's having the greater E, means can act as an acceptor, and IP value, if the ionization potential is more, can act as a donor. And the wavelength, ICT wavelengths in toluene and DMSO, and this ICT values, okay, ICT, okay, lambda max in solid phase. Now, if you see in case of second and fifth molecule, you can see the EA is more, 2.43 and 2.55 as compared to the other molecules. Okay, in case of second and fifth. Second and fifth is what here? Second and fifth. Along with quinoxaline, this is having this anthraquinone, carbonyl group, which acts as a strong electron withdrawing groups. So the electron accepting property of this core and this core is what? Greater as compared to these electron accepting moieties. So that's why electron affinity calculated theoretically in case of the second and fifth molecule is much more. Now the HOMO you can see is a max 6.70, okay, and 6.76. But if you see the other electron affinities of other, okay, acceptor systems of these molecules, in case of DA molecules, it's lesser as compared to this. So thus, if you vary see the acceptor unit, that also affects on this IP values as well as the E values. And you can see some little bit bathochromic shift, okay, due to the variation in the acceptor core and the position of carbazole group on this acceptor cores. Now let's come to the fluorescence property of these molecules, because ultimately these molecules, if can be used in the organic electronics, so they may have say the dual property like the charge transporting properties as well as the emissive property. Like if the molecule shows the green emission, can be used as an to fabricate for fabrication of the green light emitting dyes. So these are the emission spectra of compounds 1 to 8 in chloroform solvent and solid phase. The molecules emit blue to yellow rays. These molecules 1 to 8 purchase, okay, a broad against the spectrum here. So they emit from blue to what? The orange. In solid state, the emission goes up to what? Orange range. Orange in the red region also. So 467 to 565 nanometer. In solid state. Lambda wavelength of emissions of 1 to 5 varied as 1, 4, 3 in accordance with their acceptor strength 1, 4, and 3. Okay, in case of third and fourth is much more. In case of solution state, third and fourth, because as compared to 1, because this ring is what free. Now if you join this ring, okay, the conjugation increases, and you can see that again the emission in lambda wavelength of emission is what also increases in case of this condensation. Twisted system of 2 and 5 show dominant electron transfer ET character. The 2 and 5 which is having again the quinoxaline phenazine along with anthraquinone. So just I discussed that electron accepting moiety, okay, are the strong, acts as a strong electron acceptor and show the dominant electron transfer character, and hence there we can see the quenching emission through twisted intramolecular charge transfer transition. Twisted intramolecular charge transfer transitions. So there is the more, again see you can see in case of second and fifth, okay, more bulkier against these molecules are there. The twisting is what possible. So that's why due to that in case of solution state, so you can see this phenomenon that is twisted intramolecular charge transfer transition and dominant against the electron transfer takes place. Fast electron transfer takes place from donor to the acceptor, so that's why emission quenches there. In case of 6 to 8, that is the indole quinoxaline derivatives. You can see this wavelength, okay, emission of wavelength In 6 is a greater because in that case, the 6 molecule indole quinone silane, the donor is at the indole site. Okay, so that donating capacity of indole is nothing but itself is a donor. When we have this on that indole, the donor carbazole is attached, the donating property of both is what increased, and the electron transfer takes place from that donor carbazole indole to the quinone silane. So wavelength, if you see the wavelength emission of 6 is more greater as compared to 8 and then 7. Accordance with the variation in acceptor strength and donating strength of carbazole based on its position, okay, on the core molecule. So when it is on the indole side, is more as compared to when the carbazole position is on the acceptor side. Now this is what a table you can see here, the emission data of 1 to 8 in toluene and DMSO and in solid film, and you can see the stock shift also. We can see the good, again see the number of stock shift here. Okay, so there is the if you get the good stock shift, so that indicates there is no reabsorption of emitted quantas, and that is highly required in case of this applications of such molecules in OLEDs. And we can have six, you can see the band gap also, band gap calculated by using this formula. Okay, and quantum yields are also given in the bracket, in the parenthesis, with reference to the quinine sulfate. Now, if you see the quantum yield in case of molecule 6 is maximum, that is in percent, it is given 82.22. It's very, very high, okay, as compared to what your quinine sulfate. Then with this 8 molecule is a 20.74, and then in case of 4th is 18.88. So we have used in this case the various solvents to study the positive solenochromic effect, and that is correlated by, again, see the different, again, the Lippert-Mataga equation or the Richard polarity parameter. Now if you see here, the toluene, THF, chloroform and DMSO, these 4 solvents are used. You can see here the bathychromic shift of wavelength or the color changes. Like in case of 3rd molecule in toluene, it shows the cyan blue emission. But if you move from non-polar to the polar solvent, like a THF, chloroform, DMSO, you can see the wavelength in the higher. That is what the bathychromic shift you can see over here. So they show the green emission, yellow, and then at the higher value. So that means the bathychromic or the red shift you can see. So in all the molecules, you can see the positive solenoid properties. These are the emission images of 1 to 18 toluene, THF, chloroform, DMS under 365 nanometer EV elimination. And if you see here the plot B, C, okay, and D. So this positive solenochromism effect in these molecules can be explored further by Richard polarity parameters, so which is shown in B and C. That is wavelength emission versus polarity index ET30. That is called as the Richard polarity parameter. And the Stokes shift versus polarity index ET30. So here we can see the good regression coefficient, a linear regression coefficient, and that value R value is above 0.8, 0.96. So this also confirms here the solvent effect, that means the positive solenochromic effect in this DA kind of molecules. Then the D plot, you can see here the Lippert-Mataga. That is Stokes shift versus orientation polarizability. And this plot is what used to show the stabilized, it shows the stabilized ICT in polar media. That is your mostly when you compare the absorption spectra and the emission spectra, change in solvent polarity in absorption spectra on ICT particularly, there is a negligible effect. But change in polarity of solvent in case of emission of these molecules is greatly influenced. The intramolecular charge transfer, okay, state, excited state of the molecules in polar media, that is stabilized. by the polar medium of that solvent. And thus you can see the bathochromic shift. Okay, so wavelength shifted to the longer wavelength, red shift you can see. So this Lippert-Mataga, this plot, it gives us the information about the stabilized ICT state of these molecules, DA molecules in polar media. The positive solar to chromism, again you can see here the good regression coefficient here, R value is about 0.9. General solvent effect also can be discussed on the basis of this Lippert-Mataga plot, and the stabilized excited state, then ground state. Then let's see about the solid state emission properties in these molecules. You can see here the solid state emission spectra of compounds 1 to 8. If you see over here, compound 1, 3, 4, 6, 7, 8 show the good emission in their solid state. So these solid films are made here. We have taken the quartz glass plate on which we coated by using a spin coater. Okay, a very dilute solution of these compounds are taken, okay, at a particular RPM speed. So these solutions of these compounds, these are coated on a quartz glass plate, and then we took the emission, okay, and the visible lamp as well as the UV lamp. Now solid state emission exhibited by DA pairs of 1, 3, 4, 6, 7, and 8. Okay, you can see here the pictures of solid powders of these molecules in visible lamp as well as the UV lamp. Now you can see UV here, first, third, fourth, 6, 7, 8 compound, they show the emission in their solid state, in solid film also, and solid powders also. The second and fifth compound, as they have this phenoxylene and anthraquinone moiety, or the phenazine and anthraquinone moiety. Okay, so charge transfer takes place very fast. So that's why emission in quenching in emission is what we have seen in the solution state as well as here the solid state. Okay, so these are non-emissive molecules in their solid state, and the rest of the molecules are emissive, and that indicates the presence of the aggregation-induced emission properties in these molecules, which would be advantageous for their application in organic electronics. Now, this aggregation-induced emission property is studied by using the solvent mixtures. Here, if you see these images, emission images showing AIE effects with varying percentage of water fraction in THF water mixtures, 10 to the power minus 5 mole. These images you can see. And right side, you can see the plot of emission intensity versus percentage of water fraction in THF water mixture. In case of molecule 1, 7, and 8. Now here in pure THF, the molecules are emissive due to intramolecular charge transfer. But when we increase the water fraction by 10%, success 10, 20, 30, 40, 50, 60, 70, 80, and 90. Now you can see here the bathochromic shift in the wavelength and emission quenches due to the increase in polarity of that solvent. As we have seen, see the positive solar to chromism. Okay, the emission intensity, positive solar to chromism here. You can see the bathochromic shift when you increase the polarity of the solvent, as well as at the same time see the emission, it quenches in the highly polar solvent material. So that is the positive solar to chromism. So here also, so you can see the bathochromic shift and the quenching in emission when we increase the water fraction by 10%. But at a certain water fraction here, in case of compound 1, at 70% water fraction, you can see again the emission is regained. And that is nothing but due to the formation of nanoparticles of this DA molecule. Here, at this water fraction, 70% water fraction, there is little hydrophobic environment, the molecules start solidifying, but the size is at a nano level. And this you can see here, the images of these vials, okay, in visible lamp. You can see here the homogeneous suspension formation. And like in case of solid state, we have seen the emission here. In case of first, third, fourth, sixth, seventh, and eighth molecule. For AI study, we have taken first, seventh, and eighth. At 70% water fraction onwards, you can see the emission in these vials due to the formation of nanoparticles of these molecules. That means they get solidified, but particle size very, very less, nano level. And that confirms against the presence of, the fluorescence property of these molecules in their solid state. Either this is what in an aggregated state, the larger size, okay, on a film, and in this solution, mixture that is THF water at high water fraction, that's 78 to 90%, due to formation of nanoparticles. You can see here the emission is again regained, obtained. And here you can see the emission intensity versus water fraction at 60 to 70 here. This molecule 1, it shows the AIEE property. That is aggregation-induced enhanced emission. Because the emission intensity of this molecule in pure THF, which is just about 800. But at this fraction, the emission intensity enhances. It goes up to what, nearby 1000. So that's why it shows the aggregation-induced enhanced emission property. In case of molecule 7, you can see on increasing the water fraction, the decrease in emission intensity, and at 80% water fraction, you can see here the good emission due to formation of emissive nanoparticles. And this shows here, see the AI property, aggregation-induced emission. And in case of molecule 8, you can see here the 80% and 90%. Again, you can see the AI effect, but it's a very big. And between 10 to again 50 or 60 water fraction, you can see the dark DICT state. So where the increase in water fraction, that is a non-polar solvent, highly polar water solvent, okay, have effect on the emission of these molecules, okay, and that phenomena we can see the twisted intramolecular charge transfer. So this is what the AI property which we can observe in case of this molecule. First 7 and 7-8 is the indole quinoxalin derivative, and first is your I'll go to the structures of this molecule. First is this one, a quinoxalin. Here you can have this carbazole and phenyl, and these are the rotatable two rings, CN bond. This molecule can rotate at the CN bond and this CC here. So greater, again, see the rotation, you can see there is the RR effect is there in case of this, the solid state. It will be explained. I will explain it in the next slide in the theoretical studies. And that is in case of the 7th and 8th molecule, have this indole quinoxalin and a pyrido pyrazine indole molecule. Now this AIE and the size dependent emission of these nanoparticles. If you see here, again, the emission at this 70% water fraction is much higher. Then 80% it lowers. And it's due to the presence of, again, see the size and shape and the number of nanoparticles and the morphology of nanoparticles formed in these different water fractions. To confirm again, see this, the formation of nanoparticles. Now we carried out, see, the absorption spectra. We have taken the absorption and emission spectra of this molecule 1. This is the molecule. And you can see here at the different water fractions. And at this 60% of this water fraction, now there is a scattering of light. That indicates, and leveling of tail, it can be observed. Scattering of light, and because of that, leveling of tail in this absorption spectra at this from 60% water fraction is what observed. And that indicates the presence of nanoparticles, and this phenomenon is called as the mice scattering. And on the other side is the emission spectra here of one recorded in different water fractions. So at 0% here in THF, the molecule is emissive. But at 70%, we can see the AIE property, that is aggregation-induced enhanced emission property. And if you check it at 80% and 90%, again see the emission, okay, decreases. And that is due to what? Again, see the size, because of, see, the size dependent emission here. Maybe the particle size of that nanoparticles of that molecules, okay, formed at an 80% water fraction, okay, the size is much more as compared to the nanoparticles formed at 70%. And this is what again confirmed by using the DLS plot, dynamic light scattering properties. Okay, DLS studies obtained in case of first molecule from 70 to 90%. If you see at 70% here, maximum AIE phenomena you can see, where the nanoparticle size of these molecules is 119 nanometer. Then in case of at water fraction 80%, okay, it's 124.6 nanometer. And 90% water fraction, again, you can see the green line over here, it's more, again, 127.6 nanometer. So the change in the different particle size, there is again see the morphology changes can be again see the occurs, and because of that, you can see here the change in emission intensity, okay, in this size dependent, okay, AI studies. Okay, so this again see the mice scattering here confirm the formation of nanoparticles, and the size of the nanoparticles can be obtained by using this DLS study. Okay, with good this PDI indices. Now the quantum in case of this is the plot of relative quantum yield of in case of 1, 3, 4, 6, 7, and 8 molecule versus solvent composition of THF mixtures. Okay, again here we use the reference as a quinine sulfate. Now in THF, pure organic solvent, all the molecules they show the emission. But when we increase the water fraction, we can see here the TICT phenomena. That means the molecules they are in their isolated states, free state. But when after see the 60% of water fraction, the molecule it starts okay aggregating and forms the nanoparticles. So this is in case of the first and 7th and the 8th. You can see here the in case of first molecule AIE property, in case of 7th is the AIE, and in case of this 8th is the weak AIE. So here the emission intensity or the quantum yield, okay, of these nanoscopic aggregates is what found much better, and it is comparable with the quantum yield obtained in case of synthetic solid state, that is the thin film state. So thus this molecule they have this AIE phenomena as well as the good quantum efficiency, and thus can be used as the nanoparticles, emissive nanoparticles, okay, in various optoelectronic applications. Now that is about the whole photophysical properties like absorption property, emission property, and the AIE studies based on what the DA architecture in this molecule 1 to 8. Now let's come to these electrochemical studies of these molecules. Now we carried out cyclic voltammetry of 1 to 8, where you can see the to study the redox properties of these molecules, where you can see in CV in the oxidation as well as the reduction peaks. That further indicates the formation of DA architecture in these molecules. And we have calculated the homo-lumo level by using this formula. That's E homo is equal to minus oxidation peak potential minus redox potential of ferrocene couple used as a standard here, plus 4.8 is the standard potential of this ferrocene, okay, So if you put these values here and we get, you can calculate the HOMO and LUMO. Now HOMO, these are quite against this, the lower, okay, that is about 5.5 or 5.6. And LUMO levels are quite lower. That means the LUMOs, if the LUMOs of the molecules or DA kind of molecules or such organic molecules, which lies between 3 to 4 electron volt, so then such molecules can act as an N type of molecules or the electron transport molecules. And if the HOMO is got towards 5.2 or 5, near 5, so then that can act as an P type material or pole transporting material. So on the basis of this calculated HOMO and LUMO level, okay, so these LUMOs of these molecules or LUMO energy levels, okay, these are comparable, well comparable with the reported electron transporting molecules. So, and the whatever the band gap we obtained is below 2.5. So on the basis of this, we can say that this molecule could act as an N type or electron transporting materials. So this is the role of cyclic voltammetry in redox properties study of these molecules, and to confirm the HOMO-LUMO levels and to claim these molecules as an N-type materials with good electrochemical band gap below 2.5. Now these molecules additionally they possess the good thermal properties, okay, about 200 the melting points. And if you see this thermal study was carried out by thermogrammetric analysis, and you can see the 5% and 10% weight loss, it is about 200. So these molecules can have CBC or have the good thermal properties that can be used in applications in various optoelectronic devices where they have to sustain up to 80 degrees centigrade temperature. Okay, but this melting point is about 200 and they have the good temperature, decomposition temperature. So it can be used as a in OLEDs also. Now, to confirm against the TDF characters, thermally activated delayed fluorescence, theoretically, we use the Gaussian software. TDDFT studies were carried out using this software. And with the help of this the geometries in these molecules are taken here second and fifth. So fifth is again, see your phenazine having anthraquinone moiety. So there's this bulkier moiety, okay, where these two rings are joined here, and the first molecule where these phenyl rings they are free, having this carbazole as a donor, and this quinoxaline anthraquinone moiety. Okay, so second and fifth, we showed see the emission quenching in their solid state as well as the solution state. So these can act as a good TDF materials. How? These are the optimized structures of second and fifth molecule. So geometrical parameters, if you see, the molecules suggest that there is a negligible variation in bond length. Bond length, if you see here, bond length between carbon and nitrogen of carbazole, okay, 1.4 to 1.42, here 1.4. Okay, between carbon again, see here this phenyl ring is 1.48, 1.48, correct? So it is negligible, okay, variation is there, okay, between carbazole and accepted unit, okay, by changing the coning. But the corresponding dihedral angle between carbazole donor, dihedral angle if you see here, this angle, this, okay, or this angle, okay, this angle and this angle, okay. So the corresponding dihedral angle between carbazole donor and acceptor segment, these are found in the range of 50 to 128 degree. So which are slightly higher or more higher than the reported carbazole based TDF emitters. So which has it approximately 45 degree this dihedral angle. Suggest here the twisted molecular conformation of donor carbazole and this acceptor segment. So you can see over here the dihedral angle is what in case of this carbon nitrogen of carbazole 51.74. Here is 51.86. Okay, here again you can see in case of this molecule here 51.37 and here 50.64. So proper twisting is what required. These are highly twisted molecules. So that's why I showed the TDF character. Now, twisting pattern in de-assembly of dyes leads to efficiently charge separation, HOMO and LUMO orbitals. Wave function distributions causes reduction in delta EST value. Now, to get the good TDF against this character, or to get the minimized or reduced delta EST value, there is a gap between the singlet and triplet excited state. It should be minimum. Okay, it should be below 0.2. So here you can see the charge separation, it should be proper. Now these are the HOMO orbital diagram. This is the LUMO orbital in case of second, and this is in case of fifth. Now in case of second here, the mostly HOMO lies on this donor carbazole, and the LUMO level, it lies totally on this acceptor unit. So you can see here the HOMO, calculated HOMO and LUMO levels. Okay, and this is the delta energy gap between these. Okay, that we calculated using electrochemical studies also. Okay, and this is the delta EST value between singlet and triplet excited cell, that is 0.10 electron. So it's which is quite low. In case of fifth molecule, now this ring is what I can see, this fused. Two phenyl rings are fused here. You can see this HOMO lies on this donor, and LUMO, it lies on acceptor as well as this condensed phenyl. So that's why we can see just delta EST values just slightly higher than this one. Here in case of molecule second, we got 0.10, and in case of fifth, we got 0.12 electron. So thus, the small delta EST values in case of the second and fifth suggest that these molecules can act as an efficient TDF emitters. On the basis of what? The lower delta EST, that is the energy gap between singlet and the triplet excited state. And this is highly required in case of TDF emitters. So on the basis of this theoretical calculation, we can conclude that these molecules 2 and 5, other again three molecules, like see the indole derivative, 2 molecules, they have see this good TDF characters, but their delta EST values goes up to 0.3, 0.4. But in case of second and fifth, the delta EST values are very lower. So energy gap is very, very low. So that's why we can harvest the triplet excitons. Okay, internal conversion we can do, conversion can take place, okay, to the singlet exciter. So approximately 100% see the internal efficiency we can obtain in case of the second and fifth molecules. So then on this basis we can call these 2 molecules 2 and fifth as a TDF emitters. So this is the theoretically calculated again the simulated electron transition plot. So where you can see the pi to pi star and to pi star transitions and the ICT transition. Okay, and this is the wavelength and oscillator strength of HOMO-LUMO transitions in case of first, second, fifth, and sixth molecule, where you can see the ICT, intramolecular charge transfer, takes place from donor to the acceptor, that means the HOMO to LUMO, with the good oscillator strength. Oscillator values are much higher as compared to the other molecule in case of first, second, fifth, and sixth. And the percent of this against the HOMO to LUMO transition is much higher, that is 70 and 67 here, 70 or more than 65% in case of this first, second, fifth, and sixth molecule. And thus on the basis of this greater oscillator strength and greater percentage of this HOMO to LUMO charge transfer, we can we can confirm here, see against the formation of ICT, intramolecular charge transfer, in this DA type of molecules, and can say as a TDF emitters. So let's come to the conclusion of my talk. The optoelectrochemical property, that is photophysical as well as the electrochemical properties of these materials, these are significantly influenced by the extent of pi conjugation or accepting strength, and the number and substituting positions of donor carbazole moieties in these 1 to 8 molecules. Intramolecular charge transfer feature is confirmed over here that assists or helps the molecules One, to emit in blue to orange region in solution as well as solid state. Second, to exhibit noticeable positive solar diplomacy. Then strong solid state emission in case of die 1, 7, and 8 suggests AIE effect, aggregation-induced effect, by formation of nanoparticles in homogeneous DHA water suspension. Then dynamic light scattering study or analysis suggesting the formation of nanoparticles. That is, nanoparticle size dependent emission with the hydrodynamic average particle size in the range of 100 to 300 nanometer. Then the HOMO and LUMO energy level of compounds, these are comparable with reported electron transporting, that is N-type materials. Then theoretically computed small delta EST value in case of DAA, that is donor acceptor acceptor, that is second and fifth molecule acts as a donor acceptor acceptor, and 4, 7, and 8 acts as a DAD, donor acceptor donor. Structure die shows potential TDF characteristics in these molecules. And the thermal properties reveal that all the derivatives have high melting and good thermal stability, which again warrants the potential use of these molecules in various optoelectronic applications. So with this conclusion, this work just we have published in the journal, Elsewhere Journal, Journal of Photochemistry and Photobiology A, Chemistry. So just recently, in last week, this article is what appeared online. And to get more insight into these molecules and its properties and its possible applications, you can go through this journal. And let me thank all the participants, those who are kind, for their kind attention. And once again, I thank the organizers for giving me this opportunity to present this talk in the second online refresher course in chemistry organized by Department of Chemistry and HCHRDC Center of Gujarat University. Thank you very much.
Thank you very much, sir. The session has been quite an informative and encouraging one. Thank you for your valuable contribution.